Hi, I'm Larry Safran, a gRPC maintainer, and today I'm going to talk about retries in gRPC. If at first you don't succeed, try again. Then give up and scream! Sometimes client applications come up before servers are ready. Similarly, sometimes servers become temporarily unavailable or overloaded. If we were just patient and retried in these situations, we'd be able to successfully run our RPC. We could just put the retry logic into our applications, but that makes the business logic harder to understand and makes our application harder to test. It would also be one-off logic instead of taking advantage of the library's built-in functionality that has been heavily tested in lots of situations. You might ask, why don't we just always automatically retry? In order to retry, we need to have the message details available, which means storing them until success rather than dropping them as soon as the message is sent. Many applications also are time sensitive. Users want a response quickly, and even if it is that the action that they triggered failed, when retries are configured, it's great when an RPC succeeds on later tries. But if all retry attempts are exhausted, then we still need to report a failure. And this can then be much later than when the first attempt failed. There are two types of retries, and then one closely associated feature. Transparent retry happens when something goes wrong trying to communicate to the server or in the server's handling of the RPC before it gets to application logic. Transparent retry is enabled by default. Regular retry is for when there's a problem in the middle of processing an RPC. It will then start from the beginning of choosing a server and sending the RPC request. Only the configure types of failures will be retried. Hedging is a complementary feature which can be configured similarly. In hedging, instead of waiting for a failure and then retrying, hedging sends the RPC to multiple servers and then cancels the others when it gets a response. Transparent retries. These take care of RPCs that fail due to low-level races, and only if gRPC is certain that RPCs have not been processed by a server. For example, situations where the load balancer identified a server as available, but the server had started shutting down and refuses new RPCs. Once the server's application logic, callback, has been invoked, there won't be any transparent retries. It takes time for all parts of the client to react to changes, and that causes races. RPCs will be retried repeatedly until the client is eventually consistent. It will repeatedly ask the load balancer for a server target and try to use it. If its client does successfully start to send an RPC to the server, but there's a failure before the server passes the RPC to the application's callback, it will only try one more time. Note that retries are enabled without a retry policy by default, which means that gRPC will do transparent retry, which in turn means that the RPC messages will be cached in memory. The other type of RPC is the standard retry, which handles RPCs returning with recoverable error codes. In this case, gRPC successfully put a message on the wire without a clear signal that it hadn't been delivered to the server callback, so no transparent retry. This could apply to things like the server initiating load shedding. Note that you shouldn't configure cases that would always be retried. For example, illegal arguments. Standard retries are much more flexible than transparent retries. They are configured via method configurations in the service configuration of the channel. Wildcards can be used to match multiple methods. For unary or client streaming RPCs, retrying is easy since all of the messages are under the control of the client. For server streaming or BiDi streaming, to be effective, the server must actively participate in the retry. How it works. We are talking here about a case where we have explicitly configured retries. When an application calls a method on a stub to start an RPC, the gRPC client starts its work. It first saves the request message so that it can replay it later if needed. The load balancer then chooses, and initializes if necessary, a subchannel for a specific server instance. The message is then sent to a transport, which will interact with the operating system to send the message over the network to the target server using HTTP2. If at this point there is a failure, we will do transparent retries, which starts over at requesting a server from the load balancer. If the transport was able to send the request, but the server canceled the RPC with a recoverable error, then regular retry comes into play. We will wait for an exponentially increasing delay and then return to asking the load balancer for a server connection, in other words, a subchannel. In our example, we are successful on our second attempt. What if we configured a maximum of 5 attempts and the 5th attempt fails? At that point, we stop retrying and report the error. Configuration. We have 3 knobs to control the retry process, and all must be explicitly set. As you would expect, we can set the number of retry attempts before failure. You can also control the delay for the first retry and how quickly your backoff pauses between retries increasing. And you can control which status codes are considered retryable. Commonly, this is only unavailable, or sometimes both unavailable and resource exhausted. As we've discussed, configurations are done via gRPC service config, which can be specified with JSON as we see on the next slide. We aren't going to go into these topics in this video, but you can find more information about them in the retry user guide shown here at grpcio.io/doc/guides/retry. That's all for today. You can find more information about gRPC on the website, our GitHub repo, or YouTube channel and mailing list. Feel free to reach out if you have any questions. Thank you for watching.